All right, so we're doing 3.5 notes here on methods of combining functions. So this first part's pretty simple. We're going to talk about how we can take two functions and do our basic operations with the two functions. So we can do the sum of them, we can do the difference, we can do the product, multiplication, or the quotient division. So if I just took f plus g of x, it's just like taking f of x and adding it to g of x. You just add the two functions together. Same thing with subtraction. Just go in order, and same thing with multiplication, and same thing with division, provided obviously that that denominator doesn't equal 0. So let's actually work through this with some example of some functions. So here we go. F of x is x squared plus 1, and g of x is 3x minus 2. So if we want the sum of the two functions, f plus g, I just take x squared plus 1, that's f, and I'm going to add it to g, which is 3x minus 2. And now all we would do is combine like terms, and then we'd get x squared plus 3x minus 1. And that would be my final answer. Nice and easy, right? When I do subtraction, it's the same idea. I'm going to take f, which is x squared plus 1, and I'm going to subtract off. Now, when you subtract, as always, you have to subtract the whole thing, so you want to put it in parentheses, and then you want to distribute your negative so that you can make sure that everything has the right sign. Combine like terms, write your final answer. So this shows us the composition of the subtraction, or the difference of f minus g. All right, how about f times g? Well, I'll take f, which is x squared plus 1. Now, since I'm multiplying, I'm going to put them both in parentheses. And then I'll take g, which is 3x minus 2. And then I'll just multiply those out. Since they're two binomials, I have to FOIL them out. So I'll get 3x cubed, when you multiply you add, minus 2x squared plus 3x minus 2. There's no like terms to combine. And I'm done. And then the quotient is just take the f, since that's the one that's set on top, x squared plus 1, divide it by g, 3x minus 2. In this case, there's nothing that factors or cancels. You can't cancel out the x's. They're being added or subtracted to other things. So I'm done. The only thing I could simplify there is if I were to factor one of the numerator or denominators and then let stuff cancel. So adding, subtracting, multiplying, dividing, these should be pretty simple ways to combine functions. Now let's get into composition of functions. This is something you guys have done before, but it's been a while, so let me refresh your memory. This is called the composition of functions. And the symbol we see is this f, and then that little circle. It's kind of like an O, but it's not technically an O because it's really small. It's almost like a degree symbol, but in the middle there. And then g. And all this means is f of g. That's the way we say this. Okay, we say f of g. It's the composition of two functions, and basically what we're doing is f of g is taking f of the function g. So what does that mean? It means that I'm going to plug the whole function g of x into the function f of x. So you take the inside one, or you take the one on the right, the g, plug it in to the first one, the one on the left, and you're plugging it in for x. So you're taking the function of a function, which is what composition is. The domain of that will consist of those inputs in the domain of g, so you're always going to look on the domain on the inside one for which it is in the domain of f. All right, we'll talk about domain on the next page. Let's just practice a couple of basic compositions here. So we have f of x is 3x plus 1, and g of x is x squared. So they want f of g of x. Well, what does that mean? That means f, and I like to write it like this, where g of x is in a parenthesis. So f of the quantity g of x. So what does that mean? It means I'm taking all of g of x, which in this case is x squared, and I'm plugging it in to the f function for x. So instead of x here, I'm replacing x with x squared, since that's the g of x function. So what this would look like is 3 times x squared plus 1. Now that's just 3x squared plus 1, and we're done. Okay, does that make sense? Let's try it the other way. Let's do g of f. So what that is g is on the outside, f of x is on the inside. So now I'm taking the function f of x, which in this case is 3x plus 1, and I'm doing g of that function. Well, what is g of that function? Well, it just means to take it and square it. So this is just 3x plus 1 squared. Well, we know that means to actually FOIL it out. First, outer, inner, last. So that'll give us 9x squared plus 6x plus 1. Which notice, f of g did not equal the same as g of f. These two are not the same. So f of g is not the same as g of f. That means that composition is not commutative. Okay? F of g is not necessarily the same as g of f. Okay? Later we're going to see some functions where it does work, but those are special functions. For these ones, for most functions, they're not going to be the same, which is why it's really important to do it in the correct order. Okay? Let's continue on. What about when we have a number on the inside there? So what do I have here? I have the same functions. F is 3x plus 1 and g is x squared. And we want us to find f of g of negative 2. And there's two different ways we can do this. Kind of just depends on your personal preference. So the first way, I'm doing f of g of negative 2. Okay, so the first way to do this is to just evaluate g of negative 2 first. Well, what's g of negative 2? That means I plug it in here to the x squared. So that's negative 2 squared. So that's just a 4. So then what's f of 4? Well, I plug in a 4 to the f function. So that's 3 times 4 plus 1. And I get, what, 12 plus 1? So I get 13. Okay, so that's the one way. It's evaluating the g function first, plugging in and going from there. The second way is to do it symbolically first, where I just use the function first. So this is f of x squared, which is, plug in an x squared here, 3x squared plus 1. And now at the end, plug in that negative 2 that I originally had in the problem. Plug that in for x. Again, notice I'm still going to get 13 as my final answer. So when it has an actual number that you're evaluating it for, you can do it either way. You can plug in the number and evaluate it first throughout, or you can evaluate it symbolically, get that symbolic function, and then plug in the value at the end. It's totally up to you how you want to do that. Okay? All right, next part is all about domain. The biggest idea with domain when you have two composite functions, you always want to look at the domain of the one on the inside, or the first function. That's what we want to look for domain. So let's look at these two functions. I have f of x equals x squared plus 1. It's asking me for the domain and the range of f. Well, if we think about the graph of that, just off to the side, that's a parabola that's been moved up 1, right? So we know what that graph looks like, so let's think about its domain, all reals, and its range, everything above 1, correct? Okay, now let's look at g of x. And I'm going to put its information over here. That graph is the radical x graph, which is this guy. So domain 0 to infinity, range is the same. All right. Now they want us to find f of g of x. Again, I'm going to kind of rewrite this. F of g of x. That's the one on the inside. So in order to think about the domain, I have to start with the domain of g, which we figured out here is from 0 to infinity. That's my starting domain, so I can only use 0 to infinity. This is sort of my restriction here on that domain. I can only take 0 to infinity because I can't take the square root of a negative number, so I have to have positive numbers here. So let's actually work it out. That means I'm doing, what is g of x? It's the square root of x, right? Plug that in. So I plug that into my f function. I'm taking this and plugging it in for x here, which is the square root of x squared plus 1. Now this one does simplify pretty nicely, and I get x plus 1. The square root and the square cancel. And so my function is, so f of g of x is x plus 1. Now if I just graph that graph, x plus 1, I'm going to get a line, right? And a line's domain is all reals. So we would be very tempted here to say that our domain is all reals. But it's not, because you have to go back to that original domain, which said it was only positives. So I can only take positives to start this off, and it's all about that square root right there. So my domain is still just those positives from 0 to infinity. Even though this looks like a line, it's technically not because I started with only positives, so I'm only going to have those positive original x's to use. Okay, let's go the other way around. G of f, okay, well, what was the domain of f? You're always looking domain of the one on the inside. We'll go back up here. My domain of f is all reals. So I can start with all reals, okay? Once I take those all reals, it's x squared plus 1. And now I'm going to plug that into my g function, which says take the square root of x squared plus 1. Okay? And now I start to think about this. I'm like, x squared plus 1, well, it said my domain was all reals. If I plug in any real in here, is it going to work? Well, sure, I can plug in a negative. It'll square it. It'll become positive, so that'll work. So it is our domain. Okay? So my domain, all reals, since they all work in here, there's no restrictions. This has to be greater than or equal to 0, but when you start to solve that, you guys, you're going to get the square root of a negative, right? So that doesn't make a difference. So this is always positive. So we're good in terms of our domain there. Okay? All right, I'll pick up in a second on the second video.